So, Unit 4, last unit. Okay, I mean, it is, what, May the 13th? It's Friday the 13th?
Oh my gosh, we're all gonna die.
Probably not. Statistically speaking, no more bad happens on Friday the 13th than any other day. Of course, tell that to the Apollo 13 guys. But anyway, it wasn't even Friday the 13th. They were just all superstitious about them being the 13th mission and having the number 13. And like, that was actually one of the things that they were saying. Statistically, there's no correlation between bad things happening and the number 13. Famous last words. Almost. Okay, so we're going to look at simple harmonic motion today. This unit is simple harmonic motion and waves. Okay, and it will take us right up until the end of the semester, so about another 4 weeks. And then we'll have a little bit of time for review after that. So we'll be looking at what simple harmonic motion is, okay, how it can happen and be maintained, and look at two common examples of simple harmonic motion and how they work. That would be a mass on a spring and a pendulum. Okay? And the reason simple harmonic motion and waves go in the same unit is because waves are also a type of harmonic motion, and they're usually caused by a disturbance that is oscillating with simple harmonic motion. Okay? So that's what we'll be looking at during this unit here. Okay, so a playground swing, because you've all probably been on one of those, is a simple pendulum. And it oscillates back and forth, back and forth. Now, obviously, because of resistance and things like that in the real world, you have to keep pumping in order to keep moving. If you stop pumping, eventually you'll come to a stop. Okay? But for at least a short period of time, you'll be oscillating with essentially simple harmonic motion, back and forth, back and forth. Okay? A vibrating guitar string, another example of simple harmonic motion. When you pluck it, it vibrates back and forth. Okay? And it produces a sound. That's, in fact, all musical instruments are going to employ something vibrating in order to make sound. Okay? If you play like anything that has a reed in it, okay, the reed vibrates when you blow across it. If you play the drums and you hit the skin of the drum vibrates at a certain frequency. String instruments, obviously the string vibrates at a certain frequency. Okay? So everything has something that is oscillating back and forth, and then the design of the instrument helps to create interference that can amplify the sound naturally or acoustically.
What about like flutes?
A flute, it's actually the lips. Same with the horn. Okay, like the trumpet or trombone, it's all the lips of that, because you got to do that whole thing where you're like spitting into it. That's why they have a spit gun. That's what I hear. My kid plays the French horn. And I see him take the spit out. I'm like, blah. That's gross.
Isn't it the same thing as like blowing into a bottle?
Exactly. Blowing across the top of a bottle. Okay, when you blow across the top of the bottle, what you're essentially doing is making the column of air inside vibrate. And that's what you're doing with any instrument, is it's actually the column of air that starts to resonate with the other vibration that was produced. Even with a glass, like if you have a crystal wine glass, okay, and you go around the top of it, you can get it to hum. Okay, it's actually, yes, the crystal is resonating, but it's actually the air inside that's causing, that transmits the sound essentially. And you get different frequencies based on how full or empty the glass is. Okay? You can try it at home. Right? A full glass will produce a higher frequency of sound than an empty glass because the column of air vibrating is shorter, okay? So you get a higher frequency. Shorter wavelength, higher frequency. Yeah, and then we've got like a mass on a spring vibrating back and forth, so that would be like somebody who's just done a bungee jump, okay, after they kind of just oscillate up and down after the big fall, okay, that would be simple harmonic motion as well. Okay? The thing with all simple harmonic motion is that there has to be a force involved. Okay? There's the initial disturbance, and then there's a force called a restoring force that is constantly trying to, as the name would imply, restore equilibrium. Okay? If you've just got a guitar and nobody's bothered it, the strings just sit in one position. That's their equilibrium position. It's where they would naturally be undisturbed. When they're disturbed, they try to get back to that position because there's tension in the string. And when you pull it away from its equilibrium position, the tension tries to return it to its equilibrium position. The problem with restoring force is it fails miserably. It gets it back to equilibrium, but by the time it gets to equilibrium, it's been accelerating due to that restoring force. So it's built up all this speed and it goes right past equilibrium and over to the other side. And then the restoring force is like, whoa, slow down, and it's trying to pull it back to equilibrium, and it slows it down, stops it, and then starts it coming back to equilibrium. Then it accelerates back toward equilibrium, goes right through again. Okay? And it just keeps happening over and over and over again. I'll even get my dual purpose ghetto physics example out. Okay? Because not only is it good for demonstrating circular motion, it can also be a pendulum. I am saving taxpayer dollars left, right, and center with this piece of garbage. Okay? So, what we've got is if I pull this away from equilibrium, I've disturbed it, right? Normally it would just hang here. That's where it wants to be. It's where it's happy with its equilibrium position. Okay? If I disturb it, what tries to bring it back? Yeah, or at least a component of gravity acting along the arc. Okay, because the force of gravity won't increase based on where I move this to. Even up here, the force of gravity doesn't change. It's based on its mass and the acceleration due to gravity. But the further from equilibrium I get, the more direct that force of gravity becomes along the arc. When it's perfectly perpendicular, okay, the force of gravity is 100% along the arc. Okay, and as we get closer to equilibrium, that force of gravity decreases, at least a component of it along the arc decreases, until it gets back to equilibrium where it would be 0. There'd be no component of gravity along the arc here because it's now parallel. Okay, everyone okay with that idea? Okay, so if I disturb it, gravity tries to bring it back to equilibrium, but it fails. And it goes right past, and it just keeps doing that. Okay, over and over and over again. That's the nature of simple harmonic motion. There's a restoring force that varies linearly with displacement. Okay? And as we were saying, that component of gravity linearly gets bigger as I move along the arc. Okay? The same is true for a bungee cord or any other elastic object. The further I pull it, the harder it pulls. Okay? Everyone with me there? I don't know if you remember in Science 10 you did the lab with the rubber band and the spring scale. Okay? Okay, same deal. The further you pull that, the harder the rubber band would pull against you. Okay, that can act as a restoring force. Okay. All right, everybody all right with the idea of how the restoring force causes the object to accelerate? Okay, bringing it back to equilibrium. So restoring forces always act back towards equilibrium. Okay. All right. So in each case, the object has an equilibrium position. Sorry.
You said that the restoring force always tries to put the object back to equilibrium.
That's correct.
So if we will ever have to put a vector on restoring force, it would be towards the equilibrium point?
It'll depend on the situation. For a mass on a spring, it could be left and right, right? Because if it's sitting on like a air table or something like that, and it's just going back and forth, the direction could be left, right. You'd be given that, or positive and negative, something along those lines. But yeah, you would require, in some cases, a vector. Most of the time we deal with it as a scalar quantity speed. Right? The force obviously is a vector quantity, you're right. But yes, we could probably say back to equilibrium unless the question specifies it's displaced to the left. Well, then the restoring force is to the right. Yeah, restoring force is always opposite the disturbance, the direction of displacement. Okay, so we do use displacement in this when we get to Hooke's law and when we get to energy in simple harmonic motion. Then we'll have, the displacement having a vector, force will have a vector as well, but it's always opposite displacement. There's no two-dimensional vector stuff with this unit, so we want to do a tree here. Okay, so whenever the object is pulled away from its equilibrium position, a force in the system pulls it back toward equilibrium. That force could be gravity or the component along the arc of gravity, okay, as in the case of a swing or a pendulum, and it could be the stretch of a guitar string or a spring, okay. And all things that are of that nature, springs and strings and things like that, okay, they all have what we call a spring constant, and that has to do with their stiffness. Okay, like there's springs in your car that are huge. They have a very high spring constant given the nature of their job. Whereas in a clicking ballpoint pen, that spring has an incredibly small spring constant, and the two are certainly not interchangeable. Okay, can you imagine trying to click a pen with a car car spring. Okay, you have to get all your friends to lean on it. Okay, like it just wouldn't work. So all springs and all things that have an elastic nature have what we call a spring constant that's measured in newtons per meter. Okay, so how many newtons would it require to change its shape by a meter? Okay, obviously not all springs can be changed by a meter, but it's a measure of it. Okay. All right, so with this diagram here, okay, our equilibrium position would be right here, okay, right down the middle. So there's a maximum displacement this direction, okay, and you can see that the restoring force is represented by this purple arrow. It's opposite the displacement. The box moved to the left, the restoring force is pulling back towards equilibrium, or to the right, okay, and in this case where the spring is stretched, the restoring force is acting back to the left, or back towards equilibrium, okay. So restoring force and the direction of displacement or disturbance are always opposite, okay, and that's why this keeps happening, why it can become simple harmonic motion. If there were no forces that were resisting it, any drag or anything like that, it would happen forever. Okay? Now, obviously, the nature of this has been harnessed for a very long time. Very old clocks all used pendulums to keep time. Okay? The problem is no pendulum is 100% efficient. And eventually, I'll stop making this swing. It doesn't take very long for it to slow right down. Okay, now things will naturally, it'll actually swing for quite a while through this little arc here, because that's where the simple harmonic motion is more natural. Okay, it's usually in a very narrow angle. So an old grandfather clock that had a pendulum that was powering it, they wouldn't swing through like a massive arc like this. Okay, it just doesn't work. But through that narrow arc, it could be pretty efficient. But what did you have to do to a grandfather clock every morning? You had to wind it. Yeah, they usually had like a little key or something, and you wind up and put tension in this little like coiled spring, and that would throughout the day that coiled spring would get more and more loose as it kept aiding the pendulum. So if you were keeping a close eye on it, like if you had like modern equipment to time an old grandfather clock, it would keep time differently at different points in the day. Okay, as the spring would lose its compression, it would swing slower. So, time would pass more slowly at the end of the day. And at the beginning of the day, when it had more tension, you could make it swing faster. So, yeah, kind of weird, but that's the only way you could make it really effectively work. All right. Questions on that? Everyone's good with that idea? Okay, so this is an important thing to know here. The restoring force, in order for simple harmonic motion to occur, must vary linearly with displacement. Okay, that is, it gets stronger with greater displacement. Now, for a spring, that is only within its, let's say, proper elastic range. Okay, same with a rubber band. There's kind of a minimum or normal elastic range that it will stay linear. Beyond that, the force will very quickly become exponential because you are no longer stretching the rubber band in a linear elastic way. You are now permanently deforming either the rubber band or the spring by stretching it beyond its proper or useful range. Okay? So you can usually tell that. Like when we did the rubber band lab in grade 10, you could only pull it so far, and then we got a nice linear line on our graph, but a few people's last point would kind of be up a little bit because they had stretched the rubber band beyond its linear range and had begun permanently deforming it. Okay, stretching it beyond, eventually it would snap. So that can happen. Okay. With a pendulum, obviously there is also kind of a linear range through which it can swing, okay, and that's usually about 15 to 20 degrees, okay, where it'll swing fairly normally. Because if I pull it out here, does it swing along an arc? No. Well, not until it gets down here again, back in that nice range. When it's straight out here, the first thing it does is it falls straight down, and then as the string picks up slack, then it goes through the proper arc. Okay? And we'll actually do a lab on that during the unit where we actually test the effect of different things on the period of a pendulum. Okay? Do you suppose that the arc would affect the period of a pendulum? Okay, when I drop it here, do you notice that it's moving pretty fast? Does the angle make any difference? Yeah. When we do the experiment, you'll see it doesn't make any difference. Okay, the angle of arc, the angle of drop makes virtually no difference to the, I mean, with an experimental error, obviously, any difference to the period of the pendulum. Okay, and that's because the restoring force varies linearly. So when it's only pulled this much, okay, there's not a lot of restoring force. So it doesn't get a chance to really accelerate to a high velocity, so it just swings through that small arc very slowly. If I pull it up to here, that restoring force is greater, and so it accelerates to a faster speed and swings through that greater arc, reaches a faster speed at equilibrium, but still takes the same amount of time to make one oscillation. Strange but true, the things in physics. Okay, and for a mass on a spring, it just oscillates back and forth, or if it's hung from the ceiling, up and down. Okay, so the motion of objects with simple harmonic motion can be described with some terms that we're familiar with and some that are going to be new. Obviously, we already are familiar with these terms. Period and frequency, which is not listed here, but it's the inverse of period. Okay, so we'll still use that in this unit. It's still the time for one cycle. This time it's not a circle, this time it's an oscillation. Okay, now, when this pendulum oscillates, what would be the measurement of one cycle? From here to here, or from here back? Yeah, back to its starting position. That's one cycle. So it has to swing out and back to have one oscillation. For a mass on a spring, it's got to go out, up, back, or over, and back. It's got to go through one full cycle. Okay? How many times does it go through equilibrium in one cycle? Twice. Okay, so it goes through equilibrium twice in one cycle. Right, so that would be the period, or the amount of times it does that in 1 second would be the frequency. The amplitude, that's something new. We haven't talked about amplitude yet. Amplitude has to do with the maximum displacement from equilibrium. Okay? Where have you heard the term amplitude used before? Sound. Yeah. Amplitude, when we're dealing with sound, it measures volume. Okay, so amplitude measures volume. Which is why, if you want to make something louder, you use an amplifier. Okay, the amplifier makes the waves bigger. Okay, makes the oscillation bigger. Makes the oscillation of your eardrum bigger. Okay, which is something you have to be careful of when we do the waves unit. I'll actually show you just how delicate your eardrums will be by boxing your ears. No, I won't. Okay, but you guys as a generation are going to have more hearing problems than any generation before you, because you are the generation of truly portable electronics. Okay, and I mean, I don't know, I must say just about every class every day, take your buds up, take your buds up. Okay, to somebody. Okay, we didn't have that technology in my generation. We had the Walkman, which had like the orange foam things that sat on the outside of your ears and went over your head, and it was a brick, and it had a tape in it, and it took 4 AA batteries to power it, which lasted about 50 minutes, and then you got to put in another 4 AA batteries, and yeah, I can remember going up to work and on the golf course on the mower, ride on mower, and I would have to take like a package of batteries with me for the day, because turning the motor to turn the tape deck took a lot of power. Okay? You guys have more songs than I could have ever carried, and you can carry it in this little thing. It's so cool. Okay? Technology. All right. So what we start out with is we start out at equilibrium, okay? And if this thing is oscillating, okay, and so we pull it away from equilibrium and then get it going, its maximum speed occurs where? Where is it going the fastest?
In the middle.
Yeah, in the middle, as it passes through equilibrium. Because when I pull it away from equilibrium, okay, or when it's oscillating up and down, this is actually the point here at the maximum amplitude where it actually, it stops, yeah, because the restoring force has been pulling it back towards equilibrium, slowing it down, slowing it down, slowing it down, okay? Then it starts to move back, okay? So it actually reaches a speed of 0 at the maximum amplitude in both directions. Okay? So at the maximum amplitude, the speed is 0. Okay? This is something for next week, but let's see if you guys can figure this one out. What kind of energy would it have at the maximum amplitude? Potential. Okay? It's maximum amount of potential energy, only potential energy, because it's not moving. Okay? What kind of energy does it have at equilibrium? And does it have any potential at equilibrium? Nope. Because if it's a spring, the spring is neither stretched nor is it compressed. It's no longer exerting a force. Work is force times distance. We don't have any energy at equilibrium. That's why it tends to sit there. Okay? That's that point where there's no unbalanced forces. Everyone kind of follow on that? See how everything comes, it's all kind of, this unit kind of brings everything together. Okay? It talks about the period and frequency we learned in Unit 3. It talks about forces and energy and all that kind of stuff. All brings it all together in this last unit. All right, so little things to remember like that, okay, and obviously, yeah, maximum speed as we pass through equilibrium. Okay, for a mass on a spring, okay, what do you suppose affects how long it takes a mass on a spring to oscillate? Let me get a rubber band on that. Small springs. I only have slinkies. That won't work. Okay. That's not going to work either. But rubber band is way too stiff. Way too stiff. It's backfiring on me. Well, I'm worried about the heavier weight. See what happened with this weight? I'm worried about the heavier weight doing the same thing, getting me in the face. Okay. Yeah. You're right. I need a heavier weight. Go hard or go home. Okay, so it just oscillates up and down. Okay, on there. Get an idea. Okay, now I switched to this. Did the smaller one have the same period? So does mass affect the period? Okay, what else could affect the period? Right, the tension in the spring of the rubber band. These are two different rubber bands. Okay, one has a much greater spring constant than the other. Okay, the stiffer the spring or the stiffer the rubber band, the shorter the period. The greater the mass, the longer the period. Okay, so when we're looking at it, the formula looks like this. The period of a mass on a spring is equal to 2 pi times the square root of mass divided by K. K is the spring constant. Okay. Now, what do you suppose affects the period of a pendulum? Okay, acceleration due to gravity? Yes, definitely one of the things. The length of the pendulum, yeah.
The tension of the string creates by how much the mass is.
Well, the mass actually doesn't make any difference. Because what's making it go back and forth? Gravity. Do all things fall at the same rate? Okay, that's why mass actually doesn't make any difference. If I put this mass on this pendulum, change the length. That's terrible. It actually makes no difference. And again, that's one of the things we'll test in the lab. We'll put different masses on the pendulum and swing it. See, it makes no difference whatsoever. Okay, because all things fall at the same rate. All right, everybody okay with this formula? Now, if I need to manipulate this formula for any of the things that are under the root, what am I going to have to do to everything in it? Square. Yep. Okay, so just keep that in mind. It's a little bit of algebra stuff. Okay, we'll have to do that. Now, when I get a mass on a spring oscillating, okay, look at the pattern it makes. A sine wave. Exactly. This is why waves and simple harmonic motion go together. Simple harmonic motion is a wave oscillation. Okay? And so when something moves with simple harmonic motion, it can create waves, which is what I'm doing right now. My vocal cords are resonating back and forth, okay, disturbing the air around them, creating sound waves. Okay? Someone with like really good like pitch control could sing a constant notes, and they would vibrate back and forth. I won't do that to you because I like you. Okay? All right. So if I had a problem like this one where I had to calculate the period of a mass on a spring, okay, obviously using the formula itself is pretty straightforward. I just plug in the numbers, 2 times pi times the square root of 0.2 kilograms divided by 28 kilogram meters per second. And then we would get 0.53 seconds, okay, as our period there. So this would be for a mass on a spring. So the mass would be 0.2 kilograms. The spring constant would be 28 newtons per meter. Okay, we release the ball and it just oscillates back and forth. Okay, if this is done vertically, are there any other forces brought into play besides the restoring force? Gravity. So with a vertical spring, like a horizontal spring, the oscillation is identical back and forth. With a vertical spring, it goes way further down than it goes above because gravity plays a part. Oddly enough, it doesn't affect the period. Okay. So for a pendulum, the formula looks a little bit different. Okay? As we just said, the things that affect the period of a pendulum are length and the acceleration due to gravity. The longer the pendulum, the longer the period. The greater the acceleration due to gravity, the shorter the period. Okay? Because it's not going to be allowed to swing as far out with a greater acceleration due to gravity. So it'll go back and forth really, really quickly. So if I had this pendulum on the moon, its oscillation would look a lot different. Okay? So on Earth, it looks like this. Okay? On the moon, it would be like get bored yet? Okay? It would be a lot slower. Okay? Simply because the moon's gravity is 1/6 of what it is here, so it wouldn't stop it nearly as fast. Okay? Try to do the same thing on Jupiter, really, really quick. All right. Now, in terms of terminology, okay, the mass on the bottom of a pendulum is called a bob. So if you ever get a question that says the bob of the pendulum is doing this, it doesn't mean that. Okay? That's pendulum bob, plum bob, squarepants. Okay? Plum bob, squarepants, who lives in a pineapple under the sea. No, it's stuck in your head. What? It's been stuck in my head ever since I saw it. You know, the SpongeBob theme song. You know, SpongeBob, it makes you dumber by watching it. Okay, so if it oscillates back and forth, okay, like we said, the mass on the bottom is just called a bob. Okay, I'm not sure why it's called a bob. Bob's back and forth. I don't know. Okay, but that's what it's called. So if it ever refers, it tells you the mass of the bob is this much. That's probably an irrelevant number anyway. Okay, so if we're looking at calculating the period of a pendulum, okay, and we know the length is of 1.55 meters, and we're at a really high altitude, like really, 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 really high altitude, where the acceleration due to gravity is 9.71. Okay, the period would be 2.51 seconds, and again, that's just plugged in 2 pi times the root of 155 divided by 9.71. Okay. Questions on that one? See if you guys can figure that one out. This is the pendulum that's at like the Museum of Science or something like that. It can oscillate back and forth for a really long time. Okay? So determine the length of a pendulum that will swing back and forth with a period of 1 second, assuming normal acceleration due to gravity. Oh wait, I put the formula on, I forget it. Didn't even see that. Okay, so if we're manipulating this, let's just walk through the manipulation. There it is, 1, 2, 4, 8. So t equals 2 pi root L over G. So if I'm looking for L, which is what I'm looking for in this question, the first thing I have to do is square everything. Okay, that gets rid of the roots. L and G are now no longer rooted. Okay, and everything else is squared. So I want to get L by itself. I multiply both sides by G. Divide both sides by 4 pi squared. I'm left with L. Plug in my numbers. It's not a difficult manipulation by any stretch. You just have to remember to square everything. Very often, I find people forget to square t. Okay? They remember to square the 2, they remember to square the pi, they remember to get rid of the root, but they forget to square t. Okay? I'm not sure why, but it's a common mistake. Okay, this one I don't have the answers for. You can try this one. Okay, so a future astronaut lands on a planet with an unknown acceleration due to gravity. That would never happen. You would never land on a planet where you did not know what the acceleration due to gravity was, because it would make landing very difficult and dangerous. But let's just say that that's what happened. Okay, they get there and she takes out a pendulum that is 0.65 meters long and finds that the period is 2.8 seconds. Find G for that planet. Okay, so for this question here, the givens are that we don't know G. Okay, that's what we're looking for. We know the length of the pendulum is 0.65 meters, and we know that the period is 2.8 seconds. For a pendulum, period equals 2 pi times the root of L over G. If we're solving for G, we've got to square everything, so t squared equals 4 pi squared times L over G, and then to get G, we just swap t squared and G. So G will equal 4 pi squared times 0.65 meters divided by 2.8 squared. And again, the thing people forget to do is square the period on this one. All right, so 4 pi squared times 0.65 divided by 2.8, right? Yeah, 2.8 squared. All right, so the acceleration due to gravity on that planet is 3.27. Actually, we only have 2 sig digs. 3.3 meters per second squared, which would make it likely Mars, which has 1/3 of Earth's gravity. All right, everybody okay with how that one works? Okay, nothing too tough about that. Okay, these 2 questions deal with this. And this. Which is the same formula. Okay, give those 2 a try. They'll take you a grand total of less than a minute. Okay. Everybody all right with those two? T equals 1 over F, F equals 1 over T. Oh, I left the recording. Okay, thanks. Nope, we can't do that because we haven't talked about Hooke's law yet. And we haven't talked about Hooke's law yet. Okay, that one you can do. Calculate the gravitational field strength at the top of Mount Everest at an altitude of 8,954 meters if a pendulum with a length of 1.0 meters has a period of 2.01 seconds. You do not need to use little g equals big G times m over r squared here. Okay? Gravitational field strength is acceleration due to gravity, which can be calculated using a pendulum. Okay, so we got that we are looking for the period. Sorry, we're looking for the gravitational field strength. We have the period, 2.01 seconds. And we have the length, 1.00 meters. Okay, we're looking for the gravitational field strength. So, same manipulation as before. T equals 2 pi root L over G. So when it's manipulated, G will equal 4 pi squared times L divided by T squared. So 4 pi squared times 1 divided by 2.01 squared. So 4 pi squared divided by 2.01 squared. All right, 9.77. That seems like a pretty reasonable answer given the context of the question. Okay, what we got here? All right, still got like 9 minutes. Perfect. Questions on that one? Okay, is this like mathematically challenging at all? Yeah, I think so. Let's say try 1 and 2. See how we do on those.